All right. Hey, everybody. How are you doing? I hope that you're enjoying Global Hack Week so far. Give me a second here. I think I seem to be, let's see, I seem to be in the wrong layout here. Hang on. Oh, there I am. Hi, everybody. Sorry about that. Sorry to keep you waiting here for a minute. I just had a little bit of a technical difficulty um, getting the setup going for Global Hack Week, but it's great to be here with you and welcome. Hi there, Foodies Plate. How are you? Hi there, J24SC. I'm good. Thanks for asking. I have a little bit of an allergy though, so I'm a little sneezy, but that's okay. Hopefully, we'll be all right with the stream. And maybe I'll say this might be Ola, but hi there. But average DV. But yeah, why don't we go ahead and begin? We have some really cool content for today. And it's all about image classification with vision transformers. And I'm not sure if you all have heard of these models, but they can be really useful for looking at images through a computer. But I'm going to tell you a little bit first of a welcome. And I'm just going to introduce myself. I'm Steven. I work with Major League Hacking on our admissions team. And I've been doing this for about and I also work on our hackathon team as a coach, and I've been doing this for about 7 years now, since 2018. And I would say that Global Hack Week is one of my favorite things, which we started during the pandemic, actually, in order to make it more accessible for people. And so today we're going to implement a vision transformer from scratch. We'll go over some theoretical concepts behind vision transformers, and we'll even do some coding exercises. But I want to make sure that you all, by the end, understand VIT and can implement it on the CIFAR dataset, which is a huge data set of images. But before we start, let's check in. So if you haven't checked in yet, please make sure to visit this link. I'm going to actually copy it and paste it in the chat so that you can have it there too. So yeah, maybe I can just ask you all, how are you doing with Global Hack Week? Have you seen any streams that you really liked and you want to share? Tell us. Yeah, I think I remember some of you from earlier Global Hack Weeks. So how does this Global Hack Week compare? Are you thinking that you like AI a lot? But maybe it's a little too much AI. I'm not sure. Oh, cool. Hi, Zelkovitry. Good to see you. Glad to hear that you enjoy them all. That's an acceptable answer, by the way. You can say that you enjoy them all. But yeah, just love to hear from all of you about what you're thinking about. And where does the stream resources, where are they shared? Tag the Discord channel. Absolutely, I can. I'll send you on the Discord channel, or actually, I'll just send it in the link right here. We use our YouTube channel. It's called youtube.com/Major League Hacking. Okay, I hope that's the right YouTube channel. I'm almost 99% sure. Yeah, and in fact, you can see that we're live right now on this channel. And there's so much to look at here. And you can go back and read or review the past recordings. So definitely take a look if you're interested. But yeah, so why don't we now switch to the final solution code. I want to give this to you all because I often get asked for the final solution code. But I want you to just not look at this just yet, because it's gonna bias you a little bit, I think, as you go through the workshop today. I want you to kind of come at it with face value, as a blank check, and then we'll work on it together. But I often get asked for it, and I know that people get lost, and because sometimes things go too fast, or you need to step away from the computer and it's live, so you can't really. It's hard to ask to stop and go back, but please, I want you to feel comfortable to ask things in the chat. If you want to go back and look at something, it's totally cool with me. But yeah, so here's the final solution code. And now I'm just going to give you the table of contents. So it's the introduction to vision transformers, okay? And then we're going to talk a little bit about understanding transformers. And then we're going to talk about how we moved on from natural language processing into computer vision without changing our underlying approach of transformers. And in reality, we did change a few things with regard to transformers, because images are just fundamentally different than sentences and sequences of tokens, or sequences of words. But ultimately, it will all come down to the same tokenization that we'll do for computer vision as well. Okay. And so then we'll set up our environments and pre-process a little bit our data, talk about this idea of data augmentation too, which is very important in training. And then we're going to build our vision transformer. We're going to load it in from, primarily we're actually not going to build from scratch. That might be a little bit of a misnomer there, but we're going to load in a model from a previous attempt, a pre-trained vision transformer model. And we're gonna fine tune that by training it, and then we're going to evaluate the model performance. Okay, and that's going to be really the whole day today. But yeah, then I'll talk a little bit about how you might take this a step further. Okay, so here's an introduction to vision transformers. It was introduced by the Google Brain team in 2020. And I'll just show you this blog post because it's kind of cool. And I have this great GIF that I'm actually going to reference in this workshop. But the GIF tells you basically how this works. And we studied transformers. We studied transformers so much during the first 4 workshops. And now we can actually look at how that gets applied to images instead of text. You see that there's, starting with the image, we're doing tokenization, okay? So how do we tokenize an image? Well, the way that it's done in Vision Transformer algorithm is through patches. And then those patches are flattened, just like the tokens are in NLP, and moved into embedding, where we do a vector representation of the meaning of each one. And we also are going to do some positional encoding that we'll talk about. And then we have our multi-head attention, and basically our transformer block. And then there's some classification that can happen. Okay, so it's a little bit different too because it's image classification, although you can do generating text just like we would in NLP, but in their case, they did a classification, and that's what we're going to do too. And they were just really inspired by the success of these transformer models in BERT and GPT, and wanted to give that a go for the transformers in vision. And the way that transformers revolutionized natural language processing. We talked about this a little bit in previous workshops of ours, but it's really through that self-attention mechanism. And it's allowing models to weight important parts of the sequence independently of one another, and also to process all the elements of the sequence simultaneously through self-attention. So whatever the sequence length is, we can actually in parallel look at all of these elements and determine their relationship to one another. And so here's just a few key components of the transformer. We have self-attention, positional encoding, and the feed forward, which, if you remember, the feed forward is basically adding this residual connection, and the dropouts going to allow us to move from one transformer block to another, and process the outputs of the self-attention mechanism without exploding the model. So that's a really great way of thinking about it. But as I mentioned before, when we looked at that GIF, we can extend the transformer model to vision applications. And so here's a linear projection of here's the patch was what they look like. So we basically divide the image into patches. And here you've got 9 different patches, 3 by 3. And they're numbered. So they're numbered to tell the information about position, right? That's the positional encoding part. And then when you arrange them all in order, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can then flatten them out. Okay, so we'll do a linear projection to get those information content from those patches. And we basically make a giant string of data out of this image. And then I want to ask you a question now to just make sure that you're listening here. What was the original domain of the transformer model? So it wasn't always used for vision. What was it originally used for? Yeah, Zelkovitry's right. So it would be B, natural language processing. Okay. And here's another question. What is the primary function of the self-attention mechanism in transformers? It's a question. Average DD says E. That's right. No, I'm just kidding. But you're right. It's Zelkovitry. It's also B. Yeah, this is a little bit of a trick there, huh? Give you 2 B's in a row. But thank you for participating and going along with that. So let's just look at that self-attention mechanism in more detail. Check out this sentence. We have, the animal didn't cross the street because it was too tired. Well, we've actually broken it into tokens, and this is not word by word. You can see that they've actually, this tokenization is a little bit more complex than that because they have some subwords here, right? They have a didn't is broken into 2, and tired is also broken into 2, which is kind of interesting. So there's a little bit of nuance to the tokenization scheme, but each element in the sequence can attend to every other element. So that's how it has context. And so let's look at this, for example. The animal didn't cross the street because it, right? So what about it? Well, we can see that it can look at everything before it. So we have the animal. The animal is super important in these in what comes before, but then also everything after it, and that's this green part here. And in the future, street was too tired become more important for predicting the next word. So we kind of look at it in this way, and then attention scores between any 2 elements are calculated based on their compatibility. So we can just kind of look at these layers and compute what they call softmax score, which is a way to change an attention score into a probability. And that's how the model learns. Okay, there's another slide I wanted to show you, which is about the encoder and decoder structure. So this is also a key part of the transformer architecture, and it's important to know about. Encoder, we learned a little bit about encoder in some of the previous workshops on transformers. But just to give you a little bit more on this, it consists of an encoder-decoder structure in which the encoder processes the input sequence and generates a representation. So that's what we meant about some of that tokenization, and then we would have a self-attention and a feed forward that brings into a new linear layer, and then the decoder, which eventually ultimately takes those tokens and turns them back into images or words or whatever the output might want to be. All right. And so then positional encoding, just wanted to talk about this as well. Since transformers process inputs in parallel, okay, they lack a built-in sense of order. And so these positional encoding provides this by adding a unique vector to each input element based on its position in the sequence. And so one question here, is this what causes the strawberries to have 3 R's tokenization? The strawberries, that could be actually. Yes. So how many R's are there in strawberries? It could be a result of their tokenization scheme. I don't know the answer to that. But that's a really good hypothesis, actually, because tokenization, what it does is it breaks down a sentence into subunits of meaning. And so it might not determine, strawberries might be 2 subunits, straw and berries, or maybe it's just 1 subunit. It's probably not broken down into 12 different subunits or however many letters there are in strawberries. So that's a really good observation, actually, and it might be why. But okay, so let's continue, because I want to talk about positional encoding. And so we saw earlier that the self-attention score is just calculated for every single word. It doesn't really matter, where that word is in the sentence. And so unfortunately, it means that the word doesn't know exactly where it is in this sentence. I mean, based on these self-attention scores, could you tell where the word is? Pretty tricky. You might guess that it's one of these 5, but you really couldn't tell for sure. So that's where positional encoding comes in, and it's where we add a layer to our data that encodes the position of the word. And so that's just a good way to describe it. And we don't need this for some other algorithms, such as RNN, for example. But transformers, yes, we need this. And then multi-head attention, we talked about this in some of the previous workshops on transformers, but it allows the model to focus on different parts of the input simultaneously. And each head computes attention independently, and the results are combined to form the final output. So this is just another aspect of the transformer architecture, where you can just basically have multiple heads that are processing in parallel to calculate self-attention, so that the context window could be expanded, but at the same time it does require a lot of computational power, and that's why transformers are one of the most computationally intensive algorithms to run. We see these huge projects. I think that OpenAI right now is trying to raise $500 billion. I saw $500 billion for their new capital project. And the only goal of that is to train their next generation model. Okay, so it's called Stargate, and they want $500 billion for that. And it's because these algorithms are so intensive to compute, as you can see here. But I want to now go to another quiz. If you cannot imagine our first quiz there, but cannot fathom that's another number. Me neither, right? Can you imagine? That's more money than I think any human has. But yeah, so what is the purpose of positional encoding in transformers? Okay, so we got some answers here in the chat. Everyone thinks B. Oh, I see 404. Hey there, 404. Good to see you. Yeah, I keep giving everyone B's. I used to hate it when my teacher would do this at school. So I don't know why I'm doing it to all of you, but yes, D was the answer there. And how does multi-head attention improve a transformer's performance? Here's another question for you. Okay, we have A, our first non-B guess, unless you count the E guess from Average DV. Okay, yeah, I think you all are right. I think you're right that it's A because multi-headed engine helps us focus on different parts of the input simultaneously. And so thank you all for doing that quiz because now we're going to take the transformer model that we had and apply it from NLP, which we were looking at before, to computer vision. Okay, and so here the way we adapt this is by using these smaller patches and treating the input tokens as what we're going to use in our transformer. Now, there's a few things I wanted to mention, and oh, it looks like this did not come out very well. Hang on, let me fix that just really quickly because I think I can just fix that really quickly for all of you. You can barely see that, I don't think. All right. Let's just refresh this here. There we go. Okay, so CNNs. There's another algorithm called CNN. Oh, VIT is just vision transformer. But CNN is another really popular algorithm that is used for computer vision and detecting images. And yeah, thank you. Convolutional neural networks is what that stands for. And so CNNs will process what they call spatial hierarchies in images. And so if you look at this left-hand bullet here, CNNs use filters to detect local patterns. So they will pick up on some pattern by looking at how the data looks through some particular lens. And so they might have one lens that looks at a dog or something. I want to show you all actually a really cool example. And this is from a paper about wolves and dogs. Let's see if I can find this. Basically, they used a filter to understand, to classify the difference between dogs and wolves in their paper. Let's see here. Okay, I think I found this for you. All right. So the goal of these researchers was to find out whether a dog was it a husky or a wolf? Okay, and so I'm going to show you this this publication. All right, and let me try to show you an example of what they did. Okay. Jeez. Okay, so they were trying to sort dogs and wolves, right? And so let me show you what they ended up doing. Can you all see this? So they used a CNN algorithm and they looked at training data, and this was the filter that was most valuable, most important in the convolutional neural network for predicting whether it was a husky, which is a type of dog, a pet dog, or a wolf. And take a look at this filter. What are you noticing about this filter? What is it? What is the filter focusing on, and what is it ignoring? And is it what you would expect? Convoluting nameless nuisance. What an interesting, interesting name there. And focusing on the mewing. Oh my gosh. Yeah, classifying on the basis of snow. Exactly. That's what it was. So if we actually ignore all of the mewing, as you say here, you ignore the entire face, and you look at the snow and say, okay, well, if there's snow, it must be a wolf, and if there's no snow, then it must be a dog. Okay, so yeah, this was actually classified as a wolf, this image. And so sometimes you do see a bias in your machine learning algorithm, and that's just what I wanted to highlight here. But anyway, this example shows how the filter approach works. So they would look at this filter, so it extracts just the parts of the image that seem to be really predictive, and then it computes a score for that. And then there might be multiple filters that need to be checked, but this is just an example of one filter. But going back to our differences between CNNs and VITs, we aren't doing this whole filter thing. Yeah, we're doing VITs. So they're going to use self-attention to look at all of the dependencies across the image, not just one filter, but actually analyze the whole image at once through self-attention. Okay. And yeah, I hate this too. I hate when my husky runs into snow and becomes a wolf. But anyway, it just goes to show you always have to double check your work, right, when you're doing machine learning stuff. But why do these work? I'll tell you, they excel in understanding a complex visual scene and can process the entire image. And generally speaking, these VITs can outperform traditional CNN. So I think they're one of the best, if not the best, algorithm for image classification. Okay, and so let's just take a look at this graph from the blog post from the Google Brain team, where they compare the results of VITH, which is their sort of like high model, their pro model for VIT, and they compare it against the previous state of the art on various data sets. Okay, and so you can see they have a lot of different image data sets. One of them is CIFAR 10, which is what we're going to do today. We're not going to really hit that 99.5%, but we're going to get pretty close. And that is great news. As you can see, they're excelling over that in many cases. So now I want to show you another quiz and ask, how do vision transformers process images differently from CNN? Maybe you can answer that question. All right, so a little bit of confusion on this one and not as many answers coming through, but this is correct. Zelkova treated by treating images as sequences of patches. So we're just trying to apply that same sequence knowledge from transformers to images. And next question, what is one advantage of VITs over CNNs? All right, there's a few people saying D, and you would be right. So they can capture long range dependencies more effectively. And what that means, what I mean by that is if there is some relationship in the image that is not obvious, or it's not one of the main relationships that you can capture with a few filters, um, these long range dependencies could be captured way more effectively with the Vision Transformer algorithm. And it can also allow for nonlinearities in those relationships through the feed forward network, which applies activation function. So yeah, that's a great one. And we're going to practice now. We're going to actually try and do some stuff. And we have Google Colab. So go to colab.research.google.com to get that. And you might need to sign up for an account, but it should be free to sign up if you have a Google account. And we're going to install the necessary libraries in our Google Colab. So I'm going to, remember, we have the base case already. We have that final code that works. We know works. But I'm going to actually create a new notebook. So let's see, I have a few different things here. And I'm going to make a new notebook here. And I'm going to call it our, let's call it our VIT live notebook, because sometimes I like to give a live version too. Okay. And I'll share this with all of you if you want to follow along live. And J24 made a really good point, which is that the T4 GPU is free on Colab. So thank you for mentioning that. Yes, you can get a GPU for free on Colab. It does sometimes take a little bit of playing with because you have to get in line for one. And you don't get to use it for more than one session. So your session might not last more than a couple hours, but we're not going to need that. We're only going to be here for about 20 minutes on this GPU. So feel free to click this connect button in the top right here to connect to a new runtime. And you can even hit this drop-down bar, which allows you to change the runtime type. And you can check out the T4 GPU. I'm just going to check that one out. I don't use this one usually. I use A100 because I have this Google Colab subscription. But let's try it. Why not, right? And then the first thing we wanted to do was install Torch, Torch Vision, Tim, and Matplotlib. So let's get that command going. Love to see in the chat people giving advice, telling tips, helping each other out. That's why it's so great to do some of these things live, because we actually have some help from our friends in our community in pushing us to learn. So it's great to have that. And so we're installing all of this stuff. I think you might recall a lot of these from our previous workshops, but you might not recall some of them. But that's okay, you'll learn about them. And so we have the CUDA runtime downloading, all these great things downloading. And the next thing we're going to do is, while we wait for those to download, we're going to import these Python modules. And so I'll just talk about these really quickly. Torch is, of course, where we get a lot of our neural network modules and methods, such as our linear layer, which is really key for machine learning. And then Torch Vision, this is where we might get our SciFAR, or I guess this is where we get our SciFAR 10 data set, I think, and our transform for transforming those images. And Optim is where we get our Atom Optimizer, which is really important for doing our gradient descent. And then here we have our data loader, our random splitter, our TIM, which you'll find out about what that is soon, and our datetime and our matplotlib. Okay, so let's go into our code. And while we're waiting for everything to install, I'm not sure what's happening here. Okay, just finally finished installing. That's good. We'll import Torch. And we're also going to import, actually, I'm just going to say from Torch. I'm going to simplify this command a little bit. Import NN. Okay, so we have that. I think what that'll do, I think that'll actually let me just use NN. Yeah. Okay, so import NN. And we have transforms, Optim. Optim is the other one. Optim, oops. And then we also have from torch.utils. We want that, .data. Excuse me. We want import data loader. And we also want to import that random split algorithm. And then let's see, what else is there to import? There's from torch vision transform, import transforms. And we want to import data sets. Okay. And then finally we have our TIM algorithm, our TIM library, excuse me, and our datetime. Actually, I'm not sure we need datetime. I think I use it sometimes to make little wall clocks for our training. And then of course, matplotlib. So there's our import statements there. Always important to have some import statements. Okay. So now what I want to do is start with some hyperparameters, and these hyperparameters might be familiar to you. So this was our import here. And we'll say this is our set our hyperparameters. And so first, I just want to set batch size, which if you recall from our previous case, batch size is how we determine how big the command should be. A few questions in the chat. Average Devi says, could you send the pip command? No problem. So I just used this pip command to install some of those libraries. And I use this exclamation point at the beginning because that actually tells the notebook here that I want to access the terminal, and I want this to be something in the terminal. But yeah, you can do this independently in your terminal, but I just like to keep everything in the notebook. And then the next thing I wrote was the import statements, which I think these are going to turn out okay, but we'll see in a minute. I just pasted those in the chat too for you in case you want that. But remember, you can follow along live or just follow along with your with the workbooks that I sent. But so batch size, we already have that now. It's the number of training batches that we're going to do. And then LR, which would be our learning rate, we can set this to whatever we want. Usually we set it to something between 10 to the minus 3 and 10 to the minus 4, something like that. And then the number of epochs is another training variable. So this is another how many training periods will we do. This is actually how many times will we see the data. So the batch size is how many little batches of data will we make, where each batch is different, but the epochs themselves are just going through the entire data set at least once. So here we'll go through the data set in its entirety, for 10 times. And then these are some things we didn't define in our transformers workshop earlier, but image size. So we're going to define the image size to 224, which is the number of pixels for the CIFAR 10. And then actually, before we do this part, let's actually just go ahead and look at the CIFAR 10 data set. It's produced by University of Toronto. I'll send you the link for that if you want to check it out yourself. And we basically have 80 million images in this data set. And you can see that there's so much of these images. Like, for example, airplane. You can see all these airplanes here at the top. And then automobile and bird and cat. And basically, there's these 10 different categories here of images. And they're completely mutually exclusive, so there's no overlap between automobile and truck, for example. And then there's a lot of ways to import that and so far. And there's even a CFAR 100 data set, which has a lot of different classes in it. But we're just going to focus on CFAR 10. Okay, so this is what we're working with here, and each one has those 2 to 4 pixels. And so if we go back, we can look at this. 6,000 images per class, 60,000 images total. And we, before we get into this, actually, we want to continue with our hyperparameters. And there was a question in the chat from J24SC, what's LR? So LR, I'll just write a comment here. LR stands for learning rate. And this is how fast the model solves its optimization problem. And so it means that the model wants to optimize, right, and find the best solution, but it might not find the best solution on the first go. So you can have it jiggle up its parameters a little bit. And, you know, that's through what we have in the activation functions and, you know, some of these optimization routines in the Atom Optimizer. But if you do too much jiggling, you'll never settle on a solution, on a final solution. So let me put a let me put a GIF here because maybe not a GIF, but I'll show you this here. Okay, here's an image from Google Images. So you can see what I'm talking about. Now, if you have a high learning rate, it means that the model will quickly try to find a solution. So imagine that you start off on the left here. Okay, and the model thinks, okay, let's go down. Clearly, we need to go down, down, down. And it gets to this red ball. Okay, and it gets to the red ball and it says, oh, look, this is a minimum. If you have a high learning rate, it will probably stop right at that red ball, right? And so we might want to, though, you know, I guess move the model, you know, agitate it a little bit, and jump it out of that hole, because then it could find the blue ball, which is even better than the red ball. Okay, so that would be a low learning rate, because the model wouldn't just say, okay, we're done now. We're at the red ball. We found the solution. It would actually go all the way to the blue ball. Okay, so does that make sense to you, J224? I hope that's a clear explanation of what the learning rate is. I know it's a little bit complicated, but it's just a hyperparameter to indicate, you know, how hard do we want to try to find this blue ball, basically. And the faster your learning rate is, also the less training you need. Okay, because you're going to finish pretty quick. But if your training rate is super low, it's going to take longer. Okay, if you have it in between, it probably will never reach the blue ball. All right, it'll probably stop too early. So that's a good question, though. Good question. Okay, so there was another question too, I thought. Atom algorithm for stochastic optimization. Yeah, exactly. So it's that Atom Optimizer. And we'll show you a little bit about that. I think we use Atom Optimizer in this experiment. Yes, we do. And I'll show you how we pass the learning rate into the Atom Optimizer. So those two things will sort of come together in this code. All right. But we're going to go back to our code and introduce some of these other hyperparameters, one of them being the number of classes. So we discussed that the Cypher10 dataset has 10 different images, and the training ratio, which we must define, we'll define as 0.8. It means that we're going to put 80%, so we'll write this out, 80% of the images will go into training. 20% we will use to test our results. Okay, so it just means that we're going to reserve and hold just 1/5 of the data towards the whole end of training, because we want to test and see, hey, did our VIT algorithm actually work? Right? And so now a little bit of training to do. So first, this is data preparation actually. So I'm just going to make a tab that says data preparation. And we're going to start with the data transformations, all right? And so this is where we have, I'm just going to copy the code from before. We have our data transformations. So we use the transforms module and the compose method. Okay, compose, what it does is it does the following. It will resize any images that are transformed by this using our image size parameter, which is 224, which is actually the size of the model. Because if you remember our Cypher10 data set, it's 32 by 32. And so we need to transform to have the images match the exact dimensions of the model we're going to use. And the pre-trained model we have goes 224, okay, by 224. So that's why we resize. And then to tensor, it means that we're going to convert this image into a multi-dimensional array of values. And that's what we need for the machine learning algorithm. It can't just take an image in, it needs to take in numbers and matrices. And then finally, we use normalize functions. So normalize is just to make these values all within a certain range that is not too big. And the reason why we want to do that is because we don't want our model to explode. And what that means is it could run away. If it has some really high value compared to some really low value, that can cause a problem when we do our operations, because mathematically, if there's any kind of small error in the computer, then it could explode into a really big error. So all the values need to be within the same general range for that to be avoided. And then there's loading the Cypher10 dataset. So I'll just show you that one next. I'll paste that in too. Just pasting this in from our final workbook so you can follow along if you want. And so we're going to load it in. We use the datasets module and Cypher10, and we're going to put it in the data directory of our Colab notebook. So we're going to make, it's actually going to create a little directory in our files where these images will live locally. And we want training to be true and download to be true. And we're going to apply the transform right at dataset loading period. So that's one of the awesome things about this, this Torch Vision datasets, is that we can actually apply a transformation right at the time of loading, which is really cool. And then we have train size. So we're going to multiply that training ratio by our data set length. And we're going to have our validation size, which is just everything else. And that random split method, which we talked about earlier, that's going to randomly jumble the data into these training and validation sets, so that we're not always choosing the same images for training or validation. We're not, we're not biasing our model based on that. Okay, so that's this, and then we have one last thing here, which is our loaders. And so we talked about loaders in a previous Transformers workshop, but the loaders are just helping the model to load in the batches And so you can see for our loaders here, we have a training loader where we take the training data set, we split it into these batches, these 64 batches, and we shuffle it up. And number of workers is just telling us, how parallelized we want the data to come in. And that's also with the validation loader. And so we can now run this, and I'm just going to run it because it's going to download all those images. And I'll show again, this was step 3, which was just setting up the Cypher-10 data set. Okay, and now we're going to do pre-processing and data augmentation. So data pre-processing is a really important step in machine learning. It helps us resize, normalize, and augment our data. And so we did that actually. We resized to 224, and we normalized according to the values of those images. So they could have RGB values that are really large, for example. And so then we augment the data. That's another thing which we don't do here. But data augmentation is really important to know about because it can help you with your model. So probably the teams that got those 99.5% scores did some data augmentation where they basically reduced overfitting by cropping or flipping or just altering the images to make them seem like multiple images. Like think about a puppy and a puppy that's upside down, right? The model actually thinks that those two images are different, but they're not. So we can recognize that obviously that's the same image, just upside down, but the model cannot. So that's how it's good for training. And a question from Marie, how did you choose the mean and standard deviation values for the transform normalize function? I just did that basically by trial and error. So just copy the ones that I have for you there. But yeah, you can kind of see that in there. And so then here's our pre-processing and our code for doing pre-processing and data augmentation. I have it here. I don't actually implement this. We're not going to implement this today, but I just wanted to show you what it would look like to do some pre-processing and data augmentation. You could flip the images, you could rotate them, and things like that. All right. You can look at the slides for this. It might be a good exercise for another time. But what's the primary purpose of data augmentation? Does anybody know? And Marie says D, and that's exactly right. It's to artificially increase the diversity of the training data. And here's another question for you. Which of the following is a common data augmentation technique for images? Which one of these do you think would be a good thing to try if you were trying to implement one of these? All right, see A, random cropping, and that's right. Yeah, so a lot of these others are just not anything to do with data augmentation. But then we will load and fine tune our vision transformer. So we're gonna go into the code, and here's our VIT model, which is actually preloaded from one of the Google Brain models that is uploaded to TIM, and that's why we imported TIM. And then we also initialize our model. We're going to use that optimizer, and remember, we pass the learning rate into the optimizer. So that's where the learning rate comes in and relates to that other aspect there. And then we're going to add a training and validation loop. So I'm just going to add that in here. From our previous case. And it looks just like any other training and validation loop where we're going to, over the course of several epochs, we're going to load in our batches, optimize our data set, and then we're going to have some plot of the training data and its loss. And so I'm just going to run this, but it's not going to finish in time because we are out of time, and it's time for today in Global Hack Week. But why don't you try this on your own? Run this on your TPU and see what you get. I'll show you the answer. Here's what it looks like if we were to just speed up the training. You see, over time, our training loss goes down. And so we are getting up to this loss where it's less than 5%. So we're getting up to 95+%. It's pretty good. Not as good as the Google Brain team, but pretty good. So everybody, thank you so much once again for joining. Stay tuned for the next workshop, which is Today in Global Hack Week. And don't forget to fill out our feedback form. This is really important. Okay, it helps us know what you think of Global Hack Week. So thank you again, everybody, for coming. It was great to see you, and I hope you have a great rest of the week. Take care.